Here are the answers to homework number 8 that you turned in last Wednesday. I posted a couple videos on YouTube, and one of them involved those two glasses of water next to each other that I was dropping food coloring into. And I asked you to tell me what you thought was going on in the left glass versus the right glass, because the food coloring didn't sink as much in the left glass. So how could you explain that? Pretty much everybody got full credit on this. I just wanted to see what your thoughts were. Some of you were kind of close. Actually, in the left glass, what I had was saturated sodium chloride solution that I had filtered, so it looks like pure water, but I poured that into the glass. That was about the bottom 2/3 of the glass. And then the top third of the glass, I put cold distilled water, carefully poured it onto it. And the cold fresh water will sit on top of the salt water for quite a while if you don't mix the solutions. And on the right glass, I just had normal distilled water. But it looked like both were filled with one liquid. So what I did was, when I dropped the food coloring, it looked like the food coloring was stopping in the left glass and not sinking any further. And the reason why it wasn't sinking any further was because food coloring is water-based, and its density is about the same as water. So it would only sink as far as the fresh water went. As soon as it met the layer where the saturated salt was, it wouldn't sink any further because its density was less than the density of the salt water. And then when I stirred up the solutions at the end, you saw that you could kind of see a boundary between the two liquids in the left glass if you were looking carefully. So you can kind of see, oh, there must be some liquid that's sitting on top of the other liquid in the left glass. So most of you picked up on that, so that was good. Some of you said it was corn syrup, but you had the general idea right. Number 2, I've had online for a couple of weeks. I put that on weeks ago, talking about Le Chatelier's principle, but I wanted you to just get some practice with interpreting Le Chatelier's principle and understanding what was going on in that video. With the net ionic equation that explains why the solution turns pink when hydroxide ions are added is just this one. You add hydroxide ions, they remove the protons that are on the right side of the equilibrium. So it stresses the equilibrium on the right, so it shifts to the right, to the pink side. That's why it turns pink when you add base. Why does the solution turn pink to colorless when vinegar is added? So the opposite effect. When you add vinegar, you're supplying protons, so that's stressing the equilibrium on the right, so it shifts to the left, back toward the colorless side of the phenolphthalein. Why is the basic chemical form of the phenolphthalein pink? I just accepted any answer because I know it's kind of a hard question, but it has to do with the absorption of light of that particular structure. It absorbs light in the visible spectrum, therefore it has a color. If something absorbs light that isn't in the visible spectrum, you're not going to necessarily see a color. It will just appear white. Number 3, this problem set was all about solutions and pH and buffers. This question asks, you have a 5% by mass to volume solution of vinegar. It's got a concentration of about 0.84 moles per liter. How would you prepare 100 mils of 0.21 molar solution of acetic acid? Well, if you see that 0.21 is 1/4 of 0.84, so you really need 1/4 of 100 to dilute. So you just take 1/4 of 100, or 25.0 mils of the more concentrated vinegar, and you add water till it fills up to 100.0 mils. So you're diluting it by a factor of 4. Question number 4 was a titration problem. The reaction between sulfuric acid and sodium hydroxide is a typical acid-base reaction. You get a salt and water, but the mole ratio between sulfuric acid and base is 2:1, not 1:1, because H2SO4 has 2 acidic hydrogens, so it needs 2 equivalents of base to complete the reaction. It took 22.58 mils of base, so you convert that to liters. You multiply by the concentration of the base to get moles of base that were needed to neutralize this. And then you multiply that number of moles of base times 1/2 to convert it to moles of acid that were needed, which is half. And then the concentration of the sulfuric is that number 0.00565 moles divided by the volume of acid it took, expressed as liters. That's 0.01000 liters, and you get 0.565 moles per liter for the molarity of the acid. Number 5 asked you to identify some conjugate acids and base pairs in some acid-base reactions. So you have a strong acid, strong base reaction to give you sodium bromide and water. Obviously, the HBr is the acid, NaOH is the base. In any acid-base reaction, the acid on the left becomes a base on the right. So the bromide ion, which is bound with sodium ions, is the conjugate base of HBr. And the hydroxide ion picks up a proton from HBr to become the conjugate base of hydroxide, which is water. And so there's your conjugate acid-base pairs. Same thing going on here in the second reaction. Phosphoric acid plus ammonia, your acid plus base, gives you the conjugate base of phosphoric. It loses a proton to ammonia to become the dihydrogen phosphate ion with a -1, and the base NH3 on the left picks up a proton to become its conjugate acid on the right, the ammonium ion. Notice the charges balance and all the atoms balance as well. You have next problem was I give you a 0.10 molar solution of hydrocyanic acid. It's got a pH of 5.2. What's the hydronium ion and hydroxide ion concentration? Is this a strong or weak acid? Well, you could just look that up, or just remember HCN is not one of the 7 strong acids you memorize, so it's a weak acid. I think its Ka is like 10 to the -10th. It's pretty darn weak. To solve for the proton concentration, or hydronium, whatever you want to call it, you have to plug it into the pH equation. pH equals minus log of hydronium ion concentration, and then use the inverse log. So the hydronium ion concentration is 10 to the negative pH power, and you get 6.3 to the -6 moles per liter. The hydroxide ion concentration is just then Kw 10 to the -14th divided by that number. You get 1.6 to the -9. So you can see these numbers. You should pick up on the fact that if the pH is less than 7, it's acidic, which means that the concentration of hydronium ions is going to be higher than the hydroxide ion concentration. You can see it's almost, it's over a factor of 1,000 times higher concentration of hydronium ions than hydroxide ions. So it is clearly acidic, and you can always check your work. This number times this number will always give you 10 to the -14th back within, round off error. Number 7, similar type problem. You have a basic solution where the hydroxide ion concentration is 2.9 to the -4th. What's the pH and pOH? Notice this has 2 sig figs in the measurement, so your pOH and pH have to have 2 decimal places. That's how it works. pOH is just a negative log of that, so it's 3.54. And then the pH is 14 minus that number, 10.46. So again, you have a hydroxide ion concentration that's higher than 10 to the -7th, so therefore it's basic, which means it has a high pH but a low pOH. But they always add to 14. Number 8, what's the pH and pOH of these following solutions? This one was just, everything's 1 times 10 to some power, so you really didn't even need a calculator. You could just see, well, that's 1 times 10 to the -3rd, so the pH is 3. You had to, the proper way to report it is that has 2 sig figs, that has 1, that has 2. So your pH and pOH that you report in this for 0.0010 molar HCl should have 2 decimal places, 3.00 and 11.00. Add up to 14 always. This one I didn't really care too much about because I just gave you 1 molar HCl. The pH was 0 because the negative log of 1 is 0. And 0 plus 14 is 14. So it's a very acidic solution, which means very high pOH value, very low pH value. Again, sometimes pH can even be negative for high concentrations of acids and bases. Acids, sorry. And then this last one was a strongly basic solution, so it has a very high pH of 11.00. Again, 2 sig figs in the measurement of molarity, 2 decimal places in the pH and pOH. It's just the opposite of this one. 0.001 acid, 0.001 OH. So the pH and pOH values switch. Number 9, which solution would have a lower, more acidic pH? 0.5 molar HF or 0.5 molar H2SO4? Well, they both have the same pH, therefore they both have the same, actually, no, let me correct that. They both have the same concentration, so they both have the same concentration of acid, total acid, but the pH is going to be lower for sulfuric acid because it's a much stronger acid. The Ka of sulfuric acid is like around, I found 1,000. It's a large number. And Ka of HF is like 10 to the negative fourth something, so it's much smaller than 1. So the equilibrium constant for sulfuric is much larger than for HF, so there's a lot more protons in solution for sulfuric, same concentration. So you have a lot lower pH for sulfuric versus HF. Let's see, number 10. Write the reaction to show how ammonium chloride, which is a salt of an acid, when that dissolves, you get NH4 ions and chloride ions. So NH4 plus is a weak acid. It's a conjugate base of ammonia. Chloride ion does nothing. It's a conjugate base of HCl. NH3 is a weak base, but that's a buffer solution. When you add strong acid to a buffer, the basic part of the buffer, NH3, neutralizes it. You get ammonium nitrate, which is the same stuff that's in fertilizer. It's an explosive. You could write it as NH4NO3 or the separated ions. It doesn't really matter. Write the reaction to show how the same buffer neutralizes strong base, NaOH. So this time, the strong base is neutralized by the acidic part of the buffer. NH4 plus Cl plus NaCl gives you, you get sodium chloride. You always get water, and then you get NH3. So this one might have been a little strange looking to you because you get 3 products, and that's because the base was made up of 2 parts, not just 1. I'm sorry, the acid was just made up of 2 parts. A salt plus 1, and it was a negative 1. It was a salt. But it behaved like an acid when it dissolves. Does the pH increase or decrease a little when acid is added? It decreases a little because the ratio of conjugate base to acid changes a little. It doesn't change much, but it actually does decrease a little when acid is added. Sorry. And it increases a little bit when base is added. And if you add so much acid and base, you actually destroy the buffer. Number 11, is a mixture of hydrochloric acid and sodium chloride a buffer? No, because chloride ion is the conjugate base of HCl. Chloride ion is such a weak base, it doesn't have the ability to do anything. It can't pick up a proton, because if it did, it would become its parent acid HCl. But HCl is 100% dissociated, so it can't go in this direction from chloride to HCl. So this has no ability to neutralize protons in the solution. It's too weak of a base, so therefore this cannot be a buffer. This can be a buffer, though, a mixture of carbonic acid and sodium bicarbonate baking soda, because you have a weak acid and its conjugate base, which when baking soda dissolves, you get sodium ions and bicarbonate ions. The HCO3 negative 1 will react with any added acid to go back to the parent acid carbonic. Any carbonic acid will react with added base OH to give you bicarbonate ions. So that's again how buffers work. The acid and its conjugate base just kind of go back and forth. One's converted into the other depending on if you have added acid or base.